Hello friends. Hi. Welcome back to my channel. So today we are going to talk about Hadamard product by an example. Hadamard product gives the information of an entire function in terms of its zero roots, in terms of non-zero roots, and in terms of exponential powers. So let's discuss this thing with the help of an example, and for that example we are going to consider an entire function, and we will consider sine hyperbolic of z, and for that let me have a coffee. So let's consider example of f of z equals to sine hyperbolic z. Okay, and we will decompose this function into three parts, and what those three parts are: first part is zero roots, second part exponential terms, and the third one infinite product of non-zero roots. Okay, so this thing is something which is related to zero roots. This thing is something which is related to non-zero exponential terms, and this thing is related to non-zero roots. Okay, now let me say what is m, what is g, and what is k. So m is nothing but it's a positive integer which shows that how many zero roots are present for a function. An is nothing but non-zero roots. K is the least positive number that is smaller than the order of the entire function that we have. And g is a polynomial of degree less than or equals to the order of entire function. Okay, I know these things are little tough, but once you get habitual of this, it's not that difficult. So if we have an entire function, the first step is to find out the order of that entire function. So the order of that entire function for sine hyperbolic z is actually 1. So this is the order. Okay. Now the second step is to determine that how many zero roots are present. Zero roots means that the root of the function is just 0. But you see here that if I plug 0, we get nothing but sine hyperbolic of 0, which is 0, right? So, and we have only one zero root. The multiplicity of zero root is 1, therefore m is 1. Okay? Now, this means that the g, which is the polynomial that is present on top of the exponential term, has to be a linear order, right? So therefore, g of z equals to az plus b, right? Now, again, k is 1 because m is 1, okay? And because k is 1, this implies that the canonical factors would be of this form. Okay. Now, at this point of time, we have all the essential informations that we want to have for this Hadamard product. We have E1 because k is 1, the order is 1. We have 0 root, m is 1. Now, the only thing that we don't have now is the how many, not how many, but what are the non-zero roots of that function. So now I'm going to determine the non-zero roots of f. So for non-zero roots of f, we have to just do this thing, right? So this means that sine hyperbolic of z is equal to 0. But this is quite evident that for this, z is nothing but I pi n. Okay? Okay? And where n belongs to the whole positive number, right? So this means that technically sine hyperbolic of z is nothing but z, because m is 1, exponential of a to the z plus b, infinite product of 1 minus z to the an, z over an, but an is but nothing but I pi n, right? Into the exponential of e to the I pi n, right? Okay, so we need to determine what is a and what is b, and that's it, right? So I'm going to leave all this thing here and going to erase all the leftover. Now, let me say something over here for this infinite product. Here, n goes from minus infinity to infinity, but n is not 0. We are not including n as 0. Now, here is one interesting thing. Because n covers from negative infinity to infinity, so you can see that this thing can be written as n from 1 to infinity 1 plus z squared over pi square n square, right? Make sense? Okay. And now, so finally, what we have sine hyperbolic z is nothing but z e to the az plus b, countable product of okay. Now what we can do in this, in order to determine A and B, we can divide the whole equality by Z. Right? And now what we can do, we can take the limit as Z goes to 0. The moment we take the limit Z goes to 0, this thing becomes 1. Okay? This thing will become e to the b, and this thing will become 1, right? So, 1, this is e to the b, this is 1. So technically, we have nothing but 1 equals to e to the b, which implies that b is nothing but 0, right? Okay? So, what we have essentially sine hyperbolic z equals to z e to the az countable product from 1 to infinity of 1 plus z square over pi square and square. Now we need to determine what is A. So let me erase whatever that is not necessary over here. So I can remove this thing. Okay. Right? Now it's a little hard to determine what is A. But one slight observation can help us here. Okay? The observation is this, that sine hyperbolic of z is an odd function. Okay? I think that trick can help us. So what I will do here, if this is true for all z, then this should be true for negative z as well, right? So, sine hyperbolic of negative z is nothing but negative z e to the negative z. And if I plug negative z over here, since it is squared, so it doesn't get any temper, right? Make sense? But since sine hyperbolic, as I said, it's an odd function, therefore this negative will come out and you will get negative sine hyperbolic z, negative z e to the negative az countable product in this sense. Make sense? Right? Now you can see this, that this negative cancels out, right? Now if you compare, see, I'm going to compare this thing with this. Okay? So you can see that this z is same as this z, because all this thing is same as this thing, right? This infinite product is same as this infinite product, right? So the conclusion is this, that if these two quantities have to be same, then e to the az, which was present here, has to be same as this thing. And this can happen if and only if a is 0, right? Therefore, a is 0, and hence the infinite product is ultimately I'm going to catch up from here. In the light of the fact that A is 0, B is 0, we get sine hyperbolic of Z is nothing but Z infinite product of this thing. So this is the infinite product or Hadamard product for sine hyperbolic of C. That's it for today, guys.